Hello there, Mr. Sutton here, bringing you this AB Calculus 2-6 Part 1 homework solutions on continuity. For this problem, we're trying to write the intervals of continuity for this graph. We're going to start by making note of endpoints and discontinuities. So we see here that this graph does indeed have endpoints at -1 and x equals +2. And for discontinuities, we have a removable discontinuity here at 0, and we also have a jump here at 1. So we're just going to write intervals that go around these discontinuities and stay between these endpoints. Our first interval then is going to be from -1 to 0, and then we have one from 0 to 1, and then we finally have our last interval from 1 to 2. And note that I had parentheses everywhere, no brackets. The endpoints, you might make an argument for brackets, but it's kind of a gray area whether endpoints should count as being continuous, since it's a gray area as to whether you can have two-sided limits at the endpoints. So I just left them as parentheses. For this problem, we're trying to write intervals of continuity for this crazy-looking graph. So let's start by making note of any endpoints and discontinuities. So this graph goes forever to the right and to the left. There are no endpoints. That means that our intervals are going to begin and end with some kind of infinity. Our first discontinuity is this infinite discontinuity, this asymptote at x equals -2. And then as we move to the right here, it looks like we have a removable, a hole, at x equals 1. And right here we've got a jump at, let's see, this is 1, 2, 3, 4. And it looks like that's it. So we're going to write some intervals that leave these things out. Our first one is going from -infinity to -2. And then after that, we're going from -2 to 1, from 1 to 4, and from 4 to +infinity. On this problem, we're trying to write intervals of continuity for this graph. So let's start by making note of endpoints and discontinuities. There's no endpoint to the left, so there's going to be a -infinity for the start of our first interval. Over on the right, though, we have an endpoint at 3. So we're going to stop at 3 for the last interval. And now for discontinuities, the first one I see is at x equals 1, we have an infinite discontinuity, an asymptote there. And at x equals 2, we have this removable discontinuity. So we're going to write our intervals to go from -infinity to 3 and leave out these discontinuities. First interval will be from -infinity to 1. And then union, our next interval is going to be from 1 to 2. And then we're going from 2 to 3. And optionally, you could have put a bracket on the 3 here, but it's kind of a gray area with endpoints and whether or not you can be continuous if you only have a one-sided limit. So I put that in the parentheses, and you could go either way on that one. The rest of them, though, should definitely be parentheses. For this problem, we're trying to find intervals of continuity for this graph. There are no endpoints on this graph, but let's make note of the discontinuities. So our first discontinuity over here at, let's see, 1, 2, 3, 4. At -4, we have a removable discontinuity, and also another one at x equals -2. And then as we move to the right, we see that we have a jump at x equals 3. So our first interval will be going from -infinity to -4, then from -4 to -2, and then from -2 to +3, and then from +3 to infinity is our last interval of continuity. For this problem, we want to identify all points of continuity in the type. Now, this problem here, you might notice, is a polynomial, and polynomials are known to have no discontinuities. They're continuous everywhere, so we can say no discontinuities without any further proof. On this problem, we're trying to find points of discontinuity and what type they are. Since I'm dealing with a rational function, that means I'm on the lookout for holes and asymptotes, removables, and infinite discontinuities. To figure out which I have, let me factor out my denominator. So I can take an x out of here, leaving me with just x plus 1 inside. So things that get canceled out or could get canceled out, common factors like the x here, that's going to give us a removable discontinuity, a hole. So that's going to be x equals 0 for our removable discontinuity. Now, factors that I can't cancel out in the denominator, like this x plus 1, those are going to give us infinite discontinuities. So this is going to be x equals -1 for an infinite discontinuity. For this one, we're trying to identify points and types of discontinuities for this rational function. So with rational functions, we're always looking for holes and asymptotes, that's removable and infinite discontinuities. And really the only way you can figure out which ones you've got is by figuring out what zeroes out the denominator and what the common factors are. So we're going to start by factoring that denominator. Now I'm not sure off the top of my head what this factors to, but I'm going to take a guess here. Since I've got a 2x minus 3 up here, maybe there's a 2x minus 3 factor in this thing. So what would I have to multiply by 2x minus 3 in order to get this? Well, I'd have to multiply the 2x by an x. I'd have to multiply the negative 3 by a 4. So if 2x minus 3 is one of the factors of this, this has got to be 2x minus 3 times x plus 4. Now we can actually FOIL it back out to see if it actually works. So 2x times 4 is 8x. This in the middle gives us negative 3x. 8x minus 3x gives us 5x. Cool. So we just factored it. Nice. Okay. Well, we know these 2x minus 3's are going to cancel now. And now that the dust has settled, let's figure out our discontinuities. We have a removable discontinuity wherever we just canceled something out. So this 2x minus 3, whatever zeroes that out, is going to give us a hole, a removable discontinuity. So adding 3 and dividing by 2, we've got a removable discontinuity at 3 over 2. Next, the stuff that we couldn't cancel out that still zeroes out the denominator, that's going to give us an asymptote at x equals negative 4. So that is the location of an infinite discontinuity. On this problem, we want to know which of these functions is continuous at x equals 1. So going down the line here, ln of x, well, we know ln is a function that can handle anything except negatives and 0. So this is a continuous function if we're talking about x greater than 0. Since 1 is greater than 0, we know that ln is continuous at x equals 1. So this is a yes. And anything that does not have option 1 in it, like b and d, can be eliminated. For the next one, e to the x, this is known to be a continuous function, so that's another yes. So it's narrowed down then to c and e. Now for this last one, we have to kind of analyze what's going on inside ln of x. Remember, ln by itself is fine as long as you're only plugging in positive numbers. So we want to show that e to the x minus 1 is a positive number and a continuous number as well. So e to the x, again, we show that that was continuous because it's just known to be continuous. E to the 1, which is what we care about if we're saying x equals 1, e to the 1 is 2 and some change. So if I subtract 1 from that, I get a positive number. This means that ln of x, which can handle positive numbers, must be continuous at x equals 1. So this is a yes as well. So choice E then, options 1, 2, and 3. On this problem, we're given the graph of f, and we want to know which statement is true. So let's just go through them and eliminate what we can. Statement A, f is discontinuous at x equals 0, which is right here, because the limit as x approaches 0 does not exist. Well, the limit as you come from the left and the right, we are heading toward the same y value. That's 1 for our y value that we're heading towards. So the two-sided limit then does exist. It's 1. So this is a no for answer choice A. Let's keep going. Answer choice B, discontinuous at x equals 3, because the limit and the function value don't match. Well, let's find those. The limit as we approach 3 from the left and the right is going to be 0. The function value, f of 3, is just the solid dot up here at y equals 2. So it is true that these things do not match. So answer choice B then is a yes, and we're going to pick it in just a moment. But let's look at the others just to be sure. So C, f is continuous at x equals 5, so that's right here. Discontinuous there because the limit as we approach from the left side does not exist. Okay, well, as you approach from the left side here, you're heading toward this y value up here. That's 4. That does exist, so this answer choice is bogus. And the last one, D, f is discontinuous at x equals 6 because left side and right side limit of f prime of x are not the same. So this is kind of a trick statement here. If you look here, they're talking about the limit as you approach 6 of the slope of the function. As you come from the left, the slope has a value of 2. As you come from the right, the slope has a value of negative 1. So certainly this part of the statement is true. There's one problem, though. F is continuous at x equals 6. If you look here, there's no break in the graph. There's no holes, asymptotes, jumps, or anything else like that. So because we actually are continuous at x equals 6, this is a false statement, so that's a no. So answer choice B then is our answer for this one. For this problem, we're given this rational function, and we want to know for what value of x f has a removable discontinuity. So to figure out removables, we need to look for common factors. So let's start factoring. I'm going to factor the numerator first by taking out a 2. So that leaves me with x squared plus 7x minus 8. And then factoring the numerator, things that multiply to negative 8 and add up to 7, that would be negative 1 and positive 8. Down here, things that multiply to 8 add up to negative 9. That would be negative 1 again and negative 8. So there's our completely factored function. We notice we have a common factor of x minus 1. That means that those are going to cancel. Since we can remove that, that means we have a removable discontinuity there. So that means x equals 1 is going to be our point of removable discontinuity, which gives us answer choice A. Now this x equals 8 that was an option in one of these, that would have been an infinite discontinuity because you couldn't remove it. And this x equals negative 8, well, that just would have zeroed out the function without having any other special properties. For this problem, we want to know how many vertical asymptotes this graph has. So to figure out vertical asymptotes, we have to figure out, first off, what makes the denominator 0, and second, what makes the denominator 0 that we cannot already cancel out. So for that, we need to factor this a little bit. Since I essentially have an a squared minus b squared situation, I can take the square root of these two things and break them up into a plus and minus parentheses. So I can write x squared plus 4 and x squared minus 4 as the factorization for this. Of course, we can go a little bit further. We can't factor x squared plus 4, but x squared minus 4 we can split up a little bit into x plus 2, x minus 2. Now, once we do this, we see that these x minus 2's, if we wanted to, we could cancel them out. In any case, we know that x equals 2 is going to make this factor 0, but also this factor at the same time. Since x equals 2 makes the fraction come out to 0 over 0, that means we have a whole, or a removable discontinuity, at x equals 2. Another value that makes the denominator 0 is x equals negative 2. That would zero out this x plus 2 factor. Now, since we can't cancel that out, we're going to have a vertical asymptote at x equals negative 2, which we could also call an infinite discontinuity. And then finally, x squared plus 4, well, we can't actually solve that for 0 because x squared can't be negative. So there's no way to cancel out this positive 4 with a negative 4. So we're not getting anything out of the x squared plus 4. So then in terms of how many vertical asymptotes we have, it turns out we only have this one right here at x equals negative 2. So that's going to be choice A for 1. For this problem, we're told if f is a function that has a removable discontinuity at x equals 3, which could be the graph of f. So if we have a removable discontinuity, just in terms of trying to differentiate these graphs, the key there is recognizing that if a removable discontinuity exists, then the limit is going to exist at x equals 3. A whole, which is another name for a removable discontinuity, does not affect the limit of a function. So we're looking for a place where the limit actually exists at x equals 3. So choice A, we're approaching different things from the left and the right. So this is not a removable discontinuity. Even though we seem to have like this solid dot and we have some hole looking kind of things, this is more of a jump than anything else. For choice B, this is also a jump. The limit does not exist here at 3. For choice C, the limit does exist. We're approaching the same y value from the left and the right. So C is looking pretty good for a removable discontinuity. Choice D is clearly an infinite discontinuity. This is an asymptote, definitely not approaching the same value. So then we're going with choice C.